Hello everybody, so this is the first video for chapter 3 of the reinforcement learning course. So in the last video we discussed the value function, either state value function or action value function for a Markov decision process. And now we're gonna, and we also discussed the Bellman equation, which gave a recursive equation to compute which had to be satisfied by the value function associated with the policy. So in the next video we'll still discuss value functions, but now we will try to discuss the notion of an optimal policy. So a policy which maximizes the value of where value is the expected future discounted rewards in each of the respective states. Okay, so solving a Markov decision process or a reinforcement learning problem will mean finding a policy which achieves the maximal possible return. Okay, so recall the return is the sum of discounted rewards in the future, and we'd like to maximize its expectation. So we try to find a policy which maximizes the expected discounted returns. So to do that, well, first a bit of theory. We can define a partial ordering over the policies. Okay, so we can say that one policy pi here, and here we use this stylized symbol here. I'll say greater or equal, but it's not greater or equal. It just means has a higher order. Okay, so maybe I'll say it like this. Okay, so pi has a higher order than pi prime if for all states in the set of states the value for policy pi of state S is greater or equal than the value of the policy pi prime for S. Okay, so if we have two policies, pi and pi prime, for which the value of all states, for which for all states the value of pi prime is greater or equal to the value, the value of pi is greater or equal to the value of pi prime, then we say we have this. Okay, so pi has a higher order than pi prime. This means that the policy pi is just better or equal than policy pi prime. So why do we say this is a partial ordering? Well, sometimes if we have two policies, it might not be possible to compare them with this ordering. Okay, so for example, let's say we have two policies, pi and pi prime, and two states, S1 and S2, such that policy pi gives a higher value than policy pi prime for state S1, but we have the opposite relationship. So for state S2, pi has a smaller value than pi prime. Then in this case, it's impossible to order the two policies because we don't have neither pi having a higher order than pi prime, nor pi prime having a higher order than pi. Okay, so sometimes it's possible to compare two policies when one of the policies is better than the other for all states, but sometimes there are policies that cannot be compared according to this relationship. Okay, now we can, I'll just move this a bit here. So we will define V star, which is the function characterizing the best value that can be obtained in a given state. Okay, so for any state S, V star of S is defined as the maximum across all policies of the value, all policies pi, of the value associated with policy pi of that state S. Okay, so this is the definition for V prime of S. It's the highest possible value for that state across all policies. So it can be shown, and proofs are not given here. I've given, like, if you're interested in proving all these results, you could refer to the Putterman book, for which I gave the reference. So this book is a dynamic programming book, but it has all the formal proofs for all these results. Okay, so if you're interested in digging deeper in this topic, I highly recommend that book. So it's possible to show that for a finite Markov decision problem, there always exists a policy pi star, okay, we call it pi star, which is better or equal, and by better or equal I mean has a higher order than all other policies pi. Okay, so there exists pi prime, which has a higher order than policy pi for all policies pi. Okay, so there exists a policy which is better than all other policies, and by better it means that it gives the highest value of the state for all states. Okay, so it's not surprising that this policy, we call it the optimal policy. Okay, so this is the policy we typically want to discover. It's the policy which maximize the expected return in all states, and it can be proven that such policy exists under the finite Markov decision problem assumption. Okay, so if you have an infinity of states or actions, or you have, for example, a continuous distribution for rewards or stuff like that, then the result might break up. Okay, you probably would need additional technical conditions, but for the finite case, this always works. So because of that, there exists a policy which is better than all the others. Well, clearly v star should be the value function of that policy pi. Okay, so recall v star is the highest possible value which can be achieved for a state across all policies, but because the best policy across all policies is pi star, then v star should be equal to v pi star. Okay, maybe I'll write this. Okay, so here we should have v pi star, the value function of policy pi, let's call it pi star, should be equal to v star s for all state s. Okay, so because of that result, we typically call v star as the optimal state value function, and this v star is the state value function of a given policy, and that given policy is pi star, the one that is known to exist and give a higher value to all states. It can be shown that in some problems, the optimal policy pi star might not be unique. Okay, so sometimes for some states, there might be two actions which give the same outcome, and for this reason, the same outcome or the same value. So for this reason, sometimes there are multiple optimal policies, but there must exist at least one. Furthermore, if there is more than one optimal policy, it can be shown that all these optimal policies share the same value function, which is v star. Okay, so there's only one possible v star, which is the optimal state value function, but policies for which have this v star as their value function can be are not necessarily unique. Okay, so sometimes there might be one more than one policy whose value function is v star. Okay. Similarly, we define v star as the highest possible state value or value of a state across all policies. Well, we can define q star analogously. So q star SA, it's the maximum across policies of the action value function associated with the policy pi of state S and action A. Okay, so what this means here, what's the interpretation of Q star SA? So Q star gives the expected return when taking action A in state S in the next step, and then thereafter for all subsequent steps following the optimal policy, which is one of the pi stars. So it can be shown that we can write Q star in terms of V star as follows. Okay, so Q star, repeat. Okay, let's repeat something. So recall, this is a quick informal recall, QSA. So for some policy pi, all right, Q pi SA was equal to the expectation of RT plus 1 plus gamma G T plus 1, okay, given what we have here. And this, I'll move to here. This, using double expectation theorem, we could write it as expectation of RT plus 1 plus gamma, and then we can have another expectation of GT plus 1 given ST plus 1 was equal to S prime and ST is equal to S AT is equal to sorry, I'm a bit stuck in the corner here, given, whoops, and here, given here these conditions. Okay, and this because we had last time that the expectation of the gain at time t plus 1 was just the value function at the next time step. So this was expectation of RT plus 1 plus gamma times the value function v pi at st plus 1. Okay. And here this is a conditional expectation. I don't have place here, but this should be given the same conditions. Okay, so Q star SA, it's the expectation. Sorry, whoops. Let's have this move away. But Q pi SA is the expectation of the next reward plus gamma times the value function for pi at the next state. Okay, so because of that, I'll just let's look at it. We can do the same thing for the optimal policy. So if we replace pi by pi star, we have the optimal action value function, and here this v pi here is just replaced by v star, the optimal state value function. Okay, so this is intuitively how we obtain this equation here. Okay, I'll just remove the writing, sorry for that. Okay, so this is the intuition of how we get this relationship. So it's possible to express the what we call the optimal action value function in terms of an expectation of the next reward and of the value function, optimal value function at the next state. Okay, so here this equation, we'll use it shortly in a few slides and transform it a bit. to get a new equation which will become very useful later. Okay, so we said that the value function v pi is the value function of some policy pi. V star is the value function of some policy pi star. So because of that, it must satisfy the Bellman equation for policy pi star previously derived. Okay, so we derived the Bellman equation for a given policy pi, and this equation had to hold for any policy pi. So because it's the case, it holds for any possible policy, it must therefore hold also for the optimal policy. Okay, so for that reason, we can write the Bellman equation. So this is I invite you to review the previous video for the Bellman equation, but this is simply the Bellman equation associated with policy v pi. Okay, so this is one equation that must be satisfied by the optimal value function, but shortly in the next slides we will see a second recursive relationship which has to be satisfied by the optimal value function. Okay, so the optimal value function, yes, it satisfies the Bellman equation for a given policy pi, but we're going to see another Bellman equation that needs to be followed by the optimal value function. Okay, and this new equation, it doesn't hold for all policies, it only holds for the optimal one. Okay, so for the next formula we're going to derive, again, we don't give a proof. You can refer to the Putterman textbook if you want a formal proof. But the intuition behind the next formula reads as follows, so I'll simply read it. The following recursions will will entail that the value of some state under the optimal policy must be equal to the expected return for the best action from that state. Okay, so let's see that. So again, this is not a formal proof. If you want to prove that formally, you have to do a bit, you have to go through some more effort, but this is an intuitive way to understand that. Okay, so here, the optimal value function in state S, clearly it must be the optimal action that you can take in state S. Okay, so here, V star S, the best possible value for state S, well, it's the best action value for action A in state S. Okay, so you can compare the value of the various action in state S and then pick the one which maximizes the value, and then this maximal value will be the value of that state. Okay. Otherwise, if this wasn't the case, so if there existed an action which had a higher value than the value function, then you could simply pick this new action in that state S, and this would entail that your initial value function is not the optimal value function. Okay, so this is the first step, and then we can use this to substitute q star by the definition of the Q function. So it's the maximum across all actions of the expectation under the best policy of the reward for the next step plus gamma times the return for the next step given your current state in action. And here, once again, we can use the double expectation theorem I just outlined in the previous slide. So here, we can have a nested expectation. So the expectation is the expectation of a conditional expectation. Okay, so because this conditional expectation contains more information, so st plus 1, st and at, than the one outside, it's possible to write the expectation of this guy as a nested expectation. So an expectation of a conditional expectation of this guy. Okay, and this expectation, the expectation of the return at time gt plus 1, given the next state under the optimal policy pi, this is simply by definition pi star. This is simply by definition v star of st plus 1. Okay, so it's the optimal expected return you can obtain because you use the optimal policy. Okay, so here the only thing that's left to express the expectation, well, it's an expectation over both the next reward and the next state. So it's a sum across all possible next states and rewards of their respective probability. So the joint probability of next state and reward given current state and action of the reward plus gamma times the value function at the next state. Okay, so this is the Bellman equation which needs to be satisfied for the optimal value function. Okay, so this equation for suboptimal policy, it doesn't hold. It's only for the best optimal policy. And it says that the value function, the optimal value of some state is the maximum across all actions of, and this is the value of an action in state A. Okay, so it's q star SA. So it's the action, the value of action A in state S, which is obtained by some expectation, which involves summing for all subsequent states S prime and all rewards R. Okay, so this is the second Bellman equation, which applies only for the optimal value function, and this is a very, 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 very important equation. Okay, it's probably the most important equation in dynamic programming. Okay, so this is a theoretical equation because we're going to see that in practice it might be very hard to apply if there are too many possible rewards and states, but this will lay the theoretical foundation for what we will do in subsequent chapters. Okay, another useful equation that we will use very often is the following. So what we can do here, recall that we said the optimal state value for state S is the maximum action value in state S across all actions A. Okay, so this is the equation we discussed in the previous slide. So making that substitution in a previous equation will lead to the following formula. Before going back to equation 1 to see what it is, why is this formula is useful? It's because it gives a recursive formula for not for the state value, but this time for the action value. Okay, so it allows calculating. It gives a recursive, some form of recursive equation to calculate the optimal action value function. Okay, so what was equation 1 again? Equation 1 was the following. So equation 1 entailed that the optimal action value function was the expectation here. So one thing I noticed I forgot here it should be expectation under policy. Forget about what I just said. Okay, so because here you specify that you take action A, you don't need to specify a policy. Okay, so that's fine. Okay, so but the Q star SA is the expectation given you take action A in state S of the next reward plus gamma times the optimal value function of the next state. Okay, so we can take this equation, copy it, and paste it here. But here what we can do, instead of having V star S prime, okay, or V star ST plus 1, the optimal value in the next state, we can replace the V pi star by maximum of q star, maximum across A. Okay, so if we do that in the previous equation, here in the previous equation, this was simply v star of st plus 1. Okay, but here we saw here the v star st plus 1 can be written as the maximum across all actions of q star st plus 1a. Okay, which is what we have here. And here, instead of having a, we write a prime because a is already used for the current action here. So here this gives us an equation, a recursive equation, which allows calculating q star from the value of q star at all possible subsequent states. And this expectation, well, the only unknown quantities here are rt plus 1 and st plus 1. So the expectation is simply a sum across all possible values of the next state and the next reward, weighted by their respective probabilities. Okay, so probability of s prime and r given the current state and action of the reward plus gamma times the maximum across all actions in the next state of the optimal value function in state s prime, next state, and next action. Okay, so this equation it's very important also in reinforcement learning, and it's often referred to as the Bellman optimality condition or equation, sorry, for function q star. Okay, so this previously we had the Bellman equation for v star. Now we have some Bellman equation for q star instead. A recursive formulation to that must be satisfied by q star. Okay. So again, all these equations, they seem a bit complicated to remember. So in practice, if we want to remember them, it's often useful to draw small diagrams. So the recursion for the optimal value function can be summarized by this diagram. Okay, so I won't write the whole expression, but I'll simply summarize it. So for the recursive expression for v star s was given by the Bellman equation as the maximum across all action A of a summation over all rewards and summation over all next actions of something here. Okay, and that something, it was, okay, maybe let's write it. So it's the probability of r s prime given s a times r plus gamma v prime s prime. Sorry, sometimes I say prime, but I meant star. So this is v star. Okay, so here to calculate the value function in a state S here, you have to maximize over multiple actions. And then once for each of the actions, so you have to look over various actions, and for each of these actions, then you have to consider a sum for all possible rewards and all possible subsequent states, the following quantity weighted by their probabilities. Okay, so this first part here, maximum across all actions, and then summing over r and s prime, they justify here this backup diagram. Okay, so you have to consider all possible actions A here. These are the various arrows at the next part, the first part, and here it's a maximum, so it's not a summation. And then for each respective action, you have to compute a sum of the various rewards and next states, so R and S prime here, and then compare the result you have for all actions A and take the maximum. Okay, so you can see that this backup diagram summarizes the Bellman equation. Okay, just one quick note. Personally, I'm not super fond of these diagrams, but I see that they can be helpful to visualize what's happening. Okay, but I mean, if you don't like these and you don't want to remember how these are drawn, it's not a big issue. Okay, so you can learn reinforcement learning without dealing with these diagrams, but they can be useful if you want to understand the things. Now, what's with the right side? So let's interpret the right side diagram. So the right side diagram is due to the following equation. So Q star SA was a sum across rewards, a sum across S prime of the transition function S prime given SA of R plus gamma times a maximum over A prime of Q star. Here this has to be S prime and A prime. Okay. So here, for a given combination of state and action, the Q value function, okay, so action value function, is a sum across all rewards and subsequent states. So this is why for each of these arrows there's the reward and the state here. And then for each these reward and state, you have to consider the action A prime maximizing the value function, the action value function at the next step. So you have to consider all possible subsequent actions A prime and then maximize across these actions. So this is why there's a maximum here at this step. It's because here we have to maximize over A primes, but here these arrows there's no maximum because we can have to sum across all these arrows. Okay, so this is how we can interpret this backup diagram. So it can be useful to visualize what happens in practice with these equations. Okay. Okay, so we said that the optimal value function exists, both the optimal state value function and the optimal action value functions, respectively V star and Q star. So we said they exist, but in practice, they're not easy to calculate. Okay, so our objective in practice would be to calculate these functions, but this is not easy to calculate in practice. Okay, so for example, the optimal state value function V star is the solution to the Bellman equation we've shown. Okay, and the Bellman equation is a system of nonlinear equations. Okay, so what do we mean nonlinear equations? Let's go back here. So I'll show that this is the second Bellman equation we had. Here, maybe I'll circle it. Okay. So here, the only unknown quantity in this equation is V star. Okay, so all other quantities, the function P, it's known. So you might say, well, this is just a system of linear equations with one equation per state. Why cannot we solve them? And the answer to this is because there's a maximum operator across the actions here. Okay, so having the maximum operator breaks down linearity, and for this reason, solving this type of equation is not trivial in the sense that you cannot just apply your conventional linear algebra method to solve a system of equations to get this. Okay, so this is more complicated than that. Okay, so getting the solution for the state or calculating the optimal state value function is a very non-trivial endeavor in practice. Okay, but this is what we need to do, so we'll learn methods to try to compute or at least approximate this this function. Okay, so in the next chapter, in chapter 4, we will learn how to obtain approximations for V star which have arbitrary precision. Okay, so which become as close as we want eventually to the true value function. Okay, so this will be seen later in the next chapter, and this process is known as the value iteration procedure. Okay. So calculating the optimal value function, we're going to see it's not very easy, but assuming that we have the optimal value function V star, then one quick note, sometimes I just say value function. Okay, so typically we have the state value function or the action value function, but often when I just say value function, it has to be understood as the optimal state value function. Okay, so people, if you read papers, sometimes they just say the value function, but typically they refer to the optimal state value function in that case. Okay, so what I was going to say is V star, it's unknown in practice, but assume we know it. So let's say we are able to compute it, then getting the optimal policy becomes very straightforward. Okay, so recall, okay, from the following slides, we showed that the optimal value function in a state is the maximum across all possible actions in that state, the maximum across all possible actions in that state of the optimal action value in state S and action A. And here, this optimal action value function, we saw previously that it's simply an expectation over all subsequent state and rewards of, okay, so these are the probabilities and the expectation, but of the next reward plus gamma times the optimal value function at the next state. Okay, so this recursion gives provides a way to obtain the optimal value in state S, but then what's the optimal action in state S? The optimal action is simply the action which reaches this maximum. Okay, so in other words, if we want to know what's the optimal action in state in state S, then we simply have to calculate the optimal action value in state S and then compare the value of each action and pick the optimal one across the action. And by optimal one, I mean the one with the highest action value function. Okay, so in other words, if we know the value function V prime, we can take the right side here, we can do copy and paste it here, and then the A which maximizes this expression is the optimal action in state S. Okay, so here, assume we know V prime, V star, all these quantities inside are known, so it's possible to obtain the optimal action through this equation. Okay, as we mentioned earlier, sometimes the optimal policy is not unique, and this can be seen from the previous equation. So let's go back one slide. If there are multiple A's which give the same value for this expression here, then all these A's, these action A's, are optimal actions in state S. Okay, so it's possible that in a state there are multiple optimal actions, which means multiple actions which give an equal value or equally worthy outcomes. So in that case, the optimal policy would not be unique, and any action maximizing this expression would be optimal in that state S. Okay, so in a nutshell, if we know V star, then computing the optimal action AS in state S only requires solving a one-step maximization problem, and the one-step maximization problem is the one provided here. So here, why do we mean one step? It's because we only need to consider the subsequent state. Okay, we don't need to consider the sequence of all states until the termination of the episode. We only need to consider the next subsequent state. And here, rewards in subsequent episodes, they're kind of represented already by this V star. Okay, so this is a one-step maximization. We don't have to determine rewards or transitions in more than one step. Okay, so we said that if we know V star, computing the optimal actions in each of the states is somewhat straightforward. Now, if we assume Q star is known, well, it's even easier to get the optimal policy, because the optimal action in a state S is simply the one which maximizes Q star. Okay, so Q star is the value of each respective actions in the A in the state S. So to know the optimal action in the state S, we just have to maximize this function Q star, this action value function in that state S across all possible actions A. Okay, so if we know Q star, knowing the optimal action in each state is pretty straightforward. Okay, so this looks nice. So if we want to solve a reinforcement learning problem, it seems that this boils down to finding the optimal value function. And this value function can be obtained, okay, because we said once we know the value function, we know the optimal policy. Okay, so this is great. So what we want to do is find the optimal state value function. And here we haven't shown how yet, but we have shown that this optimal value function had to satisfy some system of equations. And in next chapters, we're gonna show how to solve these system of equations. Okay, so it seems that we're done. We have nothing besides learning how to solve these system of equations. We have nothing else to wonder about, and we've solved our problem. But as we're gonna see, this is not entirely true. There are multiple problems that are associated with solving the Bellman equations we've shown earlier. So first, in the Bellman equation, if you go back to the equations, these equations involve the function P, the transition probabilities between one state and action to a subsequent state and subsequent reward. But in practice, these transition probabilities, they are often unknown for many problems. So we cannot rely on the Bellman equation directly to find the value function, because in practice, we often don't know the function P. Second, another problem that we can run into is that if the number of states and actions and possible rewards is very, very, very large, as it is in typical problems. So for example, if you learn to play chess or backgammon or some other game, the number of states is incredibly large in these games. Okay, so for example, in this, the note below, the number of states in a backgammon game, it's approximately 10 to the power 20. So the number of states is very, 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 very large. So if we want to solve the previous system of equations, there are too many states in practice to be able to solve that exactly. Okay, so often we don't have enough computational resources to solve the Bellman equation exactly. So finding the value function in that context is difficult. Okay, we cannot solve it exactly, so we'll have to rely on other methods to approximate it, which is the objective of reinforcement learning. Third problem we can run into is the following. So in our dynamic programming setting, we had to assume that the Markov property holds. Okay, so sometimes in the conditional expectations, if you go back to class 2, at some point I had to drop some of the conditions from the nested conditional expectation inside in the double expectation theorem, and this was done because we assumed that we had the Markov property. Okay, so the dynamics, or sorry, the probabilities of the next state given a current state and current action is only influenced by these current state and action and not by the past. So if this assumption fails, then the dynamic programming approach, which is the Bellman equation we've suggested, would fail. Okay, so what we've shown is this chapter about the Bellman equation. They can be used directly only for very small scale problems which have the Markov property. Okay, so for somewhat simple problems. When the problems become much more complicated, then we need to use some tricks to approximate the value function, which don't rely exactly on the Bellman equation that we've shown here. Okay, so the idea here is that reinforcement learning methods that we will develop or study in the next chapters are meant to be explicable even if the assumptions we just presented are violated. Okay, so for example, we're going to see that even if transition probabilities they're not observed in practice or they're unknown, we can still go around that and solve the Bellman equation approximately using actual experienced transitions instead of the exact ones. Okay, so in practice, instead of calculating all or knowing all the probabilities to go in each of the respective states, then we can interact with the environment and kind of learn about these transitions or transition probabilities as we experience. Okay, so this is an idea about reinforcement learning. Okay, so the same thing applies for humans. So let's say you're a baby and you're trying to attempt or you're learning how to walk. Okay, a baby does not consider all possibilities of moving all the ways he could move his arms and all the situations he could get into. No, a baby just tries something, see if it works. If it doesn't, he's gonna try something else. Okay, so reinforcement learning is more inspired by this latter approach, where instead of calculating all the possibilities and finding the best one, instead we should have a trial and error approach where we try things out, and then by trying these things out, we eventually will figure what works and what doesn't. Okay, so this will be explained more thoroughly in subsequent chapters. Okay, so just a few slides ago, we mentioned some cases where the number of states is extremely large. Okay, so the value function or optimal policies, they can be obtained only with extreme computational cost. And by extreme, sometimes it would mean like 100 million years would be necessary to compute the solution, which is, of course, not acceptable in practice. Okay, so this highlights the importance of relying on some suitable approximations. Okay, so in practice, although we won't be able for very complicated problems to exactly know the optimal value function, if we can obtain a suitable approximation, then this might work well enough for our purposes. Okay, so in practice, we might not need to be perfect. Sometimes simply being very good is sufficient for practical purposes. Okay, so when the number of states is very small, the value function is often represented through what we call a table, a lookup table, or sometimes we call it the tabular case. So it means that we can set up a table where in this table each entry corresponds to the approximated value of the various states. Okay, so let's say we have 10 states, then we can set up a table in our programming code, and this table contains the approximate. So let's say if we have 10 states, then the entry 1 of the table would be approximated value for state 1, entry 2 would be approximated value for state 2, etc. And you would have 10 entries in that table. However, for multiple cases of interest, the number of states is much bigger than what we could handle through a table. So if, for example, we said backgammon has approximately 10 to the power 20 states, well, you won't be able to store 10 to the power 20 values in a computer. So in that case, it's impossible to represent the value function through a table. So in that case, you will need to set up parametric approximations for the optimal value function. Okay, so what do I mean by parametric approximation? So let's give an example. So, okay, let's say we have a state S here. Let's say S goes between 0 and 1. So in that case, there's an infinite number of states because the interval between 0 and 1 has an infinite number of values. So let's say the value function looks like this. Then we cannot store the value for each state because there's an infinite number of states. But let's say sometimes we could find suitable approximations. So here, maybe a straight line would be a sufficiently good approximation in that case. So in that case, instead of storing the value for all states, what we could do is to store the approximated value of the origin and of the slope of this curve. Okay, so in that case, instead of storing the value function or the value of each respective state, we could store parameters associated with the approximated value function. Okay, so this makes things much more tractable and convenient in practice. Okay, so for most of the course, we'll consider the lookup table approach because it's the easiest one to explain. But in practice, for problems of interest, we typically have to rely on approximation. Okay, so by the end of the course, there's one chapter which is fully dedicated to these approximation techniques. Okay, so in practice, if some of you want to become professionals in reinforcement learning, you'll have to know how to handle the second case here. Okay. Another useful feature of reinforcement learning is the following. So again, this we'll see in subsequent chapters, but reinforcement learning spends much more time optimizing actions in states that are frequently occurred. Okay, so let's say you play backgammon. Okay, you might think, okay, I'll optimize my possible action in all the various states, and all the states are respective positions you can encounter in a backgammon game. But the idea here is that maybe some states or some configurations of the pieces are very unlikely in practice. So because they're very unlikely, it might not be very useful to optimize your action in these states. Okay, so if you never face a given state or almost never face it, it doesn't care if you don't play well in that state. You should rather spend more time in states which are often encountered in practice. Okay, so we're going to see that reinforcement learning approaches, they typically don't waste a lot of time on states that are very infrequent in practice. They tend to spend more time on states which are frequently encountered. Okay, so we're going to see that this is a feature of reinforcement learning, and this also has implications in the approximation theory for reinforcement learning that we just discussed. It's useful to spend more calculation time where it matters, which means that in the states which are often encountered. So in practice, for example, so let's say you want to design a program learning to play chess. Well, if there's a state which is never encountered in practice, well, why optimizing it? Okay, so probably the state-of-the-art systems which play chess at a very high level, they might do very, very poorly in states that nobody encounters. Okay, because probably they haven't been optimized for these states nobody cares about. They just tend to do very well in states that are very frequent. So this completes chapter 3. This was a theoretical overview of Markov decision processes and of where we introduced key terminology about these problems. So states, actions. Also, we introduced the value function, either value function for a given policy pi or the optimal value function. And we saw that solving a Markov decision process entailed calculating the value function, and once we calculate the value function, this gives us automatically, or not automatically, but in a pretty straightforward way, the optimal policy to be followed to be able to optimize your expected discounted rewards. So this completes the lecture, and I'll see you for chapter 4.